From a straight line to time, dimensions exist to connect a point to a square, to a cube, to that cube's movement across seconds, minutes, and hours. We define and map our world through the dimensions. When you draw the path for your stick figure to walk on, you draw a line. That's the first dimension. But your stick figure has to go somewhere. Perhaps he walks through a door that you draw on the rectangle, that you draw as a rectangle. That's the second dimension. That rectangle has to go somewhere too, though. In the words of the Rolling Stones, "Gimme shelter!" shouts your two-dimensional man. But once he steps into the boxy house, now he's entered the third dimension. You see, the house is a cube, which represents three-dimensional space. Now, this is where things get dicey. As your stick figure has been walking along the one-dimensional path through the two-dimensional door and into the three-dimensional house, he's been moving the entire time through the fourth dimension, which is widely accepted in physics as time. Now, how is time a dimension, you might ask? Think of the first three dimensions as vectors in explaining a shape. Dimension 1 is length. How far has the man gone along the path? Dimension 2 is width, which can be interchangeable with height. Now we ask not only how far has the man has walked on the path, but has he gone higher or lower? And how far has he gone along that path, which it turns out is not as straight as we thought. Dimension 3 is depth. Now we ask not only has the man gone forward or backward or up or down, but has he gotten closer to us or farther away? By the time we get to the fourth dimension, we ask how long has he been going, so we can calculate not only his position, but also where he might be on the total length, height/width, and depth of his journey. The fourth dimension ties them all together. Scientists such as Joseph Weber, as well as Soviet scientists Mikhail Gertenstein and Vladislav Putsevoit, have been thinking about these concepts since the 1960s. And they all worked on developing basic ideas and prototypes to test the concept of laser interferometry. Interferometry deals specifically with the fourth dimension, time. Specifically, laser interferometry is used to measure the existence of a component of Albert Einstein's theory of general relativity called gravitational waves. Since the 1960s, many projects have been started to measure gravitational waves, such as Rainer Weiss of MIT's 1967 prototype utilizing military funding, but that project was terminated before it could become operational. In the late 1960s, prototype interferometric gravitational wave detectors, or interferometers, were built by Robert L. Forward and colleagues at Hughes Research Laboratories with mirrors mounted on a vibration isolated plate rather than free swinging. In the 1970s, Weiss tried again, as well as others across the globe. In 1981, Caltech constructed a 40-meter prototype by Ronald Drever and Stan Whitcomb that established a 1980 MIT study's feasibility of interferometers at a 1-kilometer scale with adequate sensitivity. From 1989 through 1994, LIGO, or Laser Interferometer Gravitational Wave Observatory, failed to progress technically and organizationally. Ongoing project management issues and technical concerns were revealed in NSF, or National Science Foundation, reviews of the project, resulting in the withholding of funds until they formally froze spending in 1993. In 1994, however, under the new direction of Barry Barish from Caltech, a new proposal was created with new study, budget, and project plans, and a budget exceeding the previous proposals by 40%. Barish proposed to the NSF and National Science Board to build LIGO as an evolutionary detector, where detection of gravitational waves with initial LIGO would be possible, and with advanced LIGO, probable. With a new budget of $395 million US, LIGO stood as the largest overall funded NSF project in history. The project began construction on 2 new facilities that year in Hanford, Washington in late 1994 and Livingston, Louisiana in 1995. In 1997, LIGO Laboratory and LIGO Scientific Collaboration, LSC, were formed to advance LIGO's operation and advanced R&D, including administration of the LIGO detector and test facilities, and create a forum for organizing technical and scientific research in LIGO, respectively. The LIGO Scientific Collaboration is a separate organization from LIGO Laboratory with its own oversight. The spokesperson for the scientific collaboration was none other than Rainer Weiss. Initial LIGO operations between 2002 and 2010 did not detect any gravitational waves. But if at first you don't succeed, start a multi-year shutdown to make way for enhanced LIGO, where the detectors become replaced by much improved advanced LIGO versions. Much of the research and development for the LIGO/A-LIGO machines was based on pioneering work for the GEO 600 gravitational wave detector at Hanover, Germany. In mid-September 2015, the world's largest gravitational wave facility completed a 5-year, $200 million U.S. overhaul, bringing the total cost to $620 million U.S. dollars. On the 18th of September 2015, Advanced LIGO began its first formal science observations about 4 times the sensitivity of initial LIGO interferometers. Its sensitivity was to be further enhanced until it was planned to reach design sensitivity around 2021. At 9:51 Universal Time on September 14, 2015, gravitational waves from 2 approximately 30 solar mass black holes merging about 1.3 billion light-years from Earth was detected. On May 2, 2016, members of the LIGO Scientific Collaboration and other contributors were awarded a special breakthrough prize in fundamental physics for contributing to the detection of gravitational waves. Since then, LIGO alone has detected about 300 gravitational waves, including invaluable data on the concept proposed by Einstein over 100 years ago. In 2017, Weiss, Barish, and Kip Thorne, who've been with the project since 1968, received the Nobel Prize in Physics for decisive contributions to the LIGO detector and the observation of gravitational waves. Weiss was awarded 1/2 of the total prize money, and Barish and Thorne each received a 1/4 prize. The project and the search for information on these ripples in the fourth dimension is in danger as funding for federal projects in science becomes threatened by the current administration. As of right now, the website has not been updated since September 30th due to the government shutdown. But you can get involved by helping with 2 projects geared towards detecting gravitational waves and the black holes that contribute to them. The website Black Hole Hunters, linked in the description, uses the data from the TESS satellite to study graphs of how the brightness of stars changes over time. By viewing this data, you'd be looking for an effect called gravitational microlensing. This lensing effect can indicate that a massive object has passed in front of a star, such as a black hole. By using the website Gravity Spy, you can help LIGO scientists with their gravitational wave research by looking for glitches that may mimic gravitational waves. By sorting out the mimics, LIGO researchers can train algorithms on how to detect the real thing. You can also use gelatin, magnetic marbles, and a small mirror for a more hands-on demonstration how gravitational waves move through time, with JPLs dropping in with gravitational waves activity, that I will link in the description below. This and more can be found at the website that I will also link at the description below. Last but not least, remember that when science is threatened, the future of humanity becomes unsure. The best way to ensure that science advances is by feeding the furnace that keeps the ship moving forward. This is the best way to do that is to vote. From Professor Shank's astronomy class, I'm Dylan Paul, reminding you that wherever two black holes dance, they do so through the periscope of the LIGO boat and the gravitational waves of our universe.